Okay, let's get started. Good morning, everyone. Okay, so I can observe the number of students is reduced. It is because of it's rainy, and then this class is the morning class. So I think it's not easy to wake up. Surely, so recently this is the beginning of the semester, and then I believe you have many meetings and then some associations. So I believe you are very busy recently. Okay, so and then also the COVID-19 restrictions have been removed recently. So I believe you have many meetings. Okay. So but anyway, so we need to run. Okay. We need to learn. Then we need to the logic design. Okay. So I briefly review what we learned in the previous class. Okay. So in the previous class, I briefly explained about the hardware design of the computer system, and then actually I hope you already know why we need to learn this course. Okay. This course is the fundamental course which can be helpful for understanding the hardware basic fundamental knowledge of hardware systems in computer. Also, actually, in the previous class, I explained that the modern computer systems are very complex systems. So it is because actually the computer systems are composed of many components such as GPUs, also coprocessors such as GPUs. Also, our computer system includes the memory and storage devices, also many I/O devices such as the keyboard, mice, screens, and also touch screens, something like that. So actually, computer systems are very complex system, and then if we just focus on a single chip like CPU, and then I also explained that a single CPU includes many transistors, and I explained that billions of transistors, right? So which means it's very complex system. So how can we manage these complex system? Actually, the CPUs is made by humans, not aliens. So actually, we need to manage this complex system. So firstly, I also explained that our computer systems include many layers. This, and then actually we just focus on two layers. So if we study, or if we just perform research on a computer systems, we just focus on one or two layers. Okay, and then we don't need to understand the detail, the difficult knowledge or difficult theories on the focused layer. So in the previous class, I explained about these concepts in the system design. So I explained about the abstraction, discipline, and 3 Y's of the design. I hope you can remember these concepts. So, and then I mentioned that abstraction is a very important concept in computer systems because like this. So computers are composed. A computer is composed of many layers. Then, so actually, we cannot understand every aspect of this computer system. So we just focus on the layer, and then it means we don't need to understand the detailed knowledge of other layers. So what is an abstraction? Hiding details. Okay. So if we just focus on this layer, then so we need to understand the interfaces between neighbor layers. So for example, so not to understand the logic gate and the digital logic component, we need to understand some interface between digital circuits. But we don't need to understand the concept and how to build the real circuits like CMOS circuits. But if you understand some basic concept of some other layers, then it will be helpful. So, but if you just focus on a certain research or study on one layer, then you can understand not only you can understand some detailed thing of this focused layer, but you don't need to understand the detailed concept of the other layers. So this is the concept of abstraction, and then I also explained that this abstraction concept is widely adopted in software design, also in hardware design. Okay, so for example, I believe you are a Docomo student, right? Is right? So, but if you focus on some AI applications, then we frequently use AI framework such as PyTorch, TensorFlow, something like that. But I think you need to understand how AI works if you are interested in AI applications. But most coder, I want to call coder. Most coder just focus on how to use this framework, and then they do not understand some detailed mechanism or detailed algorithm of AI application. But you need to understand, right? So that is the kind of example of abstraction. You just focus on how to use the framework, and then you just focus on some algorithm, and then some high-level operation of AI application. So then I also explain about the 3 Ys of the system design: the hierarchy, modularity, and regularity. So in order to handle the complex system like this, the Intel, it's an example of Intel server CPU. So it's very complex. It's a very complex design, and then actually this single chip includes billions of transistors. So by using this concept or this methodology, hierarchy, modularity, and regularity, then many engineers can focus on the detailed component of this complex design, and then they can assemble the design components to make the very large digital system. Intel single Intel server CPU. Okay. So how we can manage these complex digital systems. Okay. So, and then actually I skipped this slide in the previous class, and then but I'll explain now because we will about the number system of digital system today. So let's think about the digital abstraction. Then what is digital abstraction? So I mentioned that in real world, all kinds of signals are analog signals. So continuous signals, and then actually the values on these signals is the real value. So it's a real number. Okay. So actually we cannot represent this real number using the floating point number. It's because even though we use we can we represent this number like the 1.25, but this cannot be exact value of this signal. Okay. So, but this we need to represent these analog signals using digital concept like digital signals. And then, as I mentioned, actually digital signals are represented using only zeros and ones. Okay. So this is the example as I explained there. Okay. So even though there are many values and then there are many different levels in the analog signals, so we can represent this analog signal using the digital signal like the 1 0 1 0 1 0. So it's simplified, right? It's very simplified. So what is the digital abstraction? Even though our real world signal is analog signal, this is just a promise. So it's just kind of a promise or a protocol. So you can just make up some criterion such as so this is the 0 volt, and then if the signal value is over 0 volt, then we can represent this signal like the 1 of the digital signal. And then if this voltage value is less than 0 volt, then we can represent this value like the 0. So that is just a promise or just a criteria. Okay, we can just set the threshold level of the real signal, and then if a certain value is over this threshold level, then we can set the 1 as a digital signal. And then if this value is lower than the threshold level, then we can set this value is the 0. So these values are discrete values. Also, we can say that these values are simplified values. Okay? So that is the digital abstraction. Okay. So actually, as I mentioned, the values have only two different kinds of levels, 1 and 0. And then usually in a digital system, 1 means true. It's true or high. And then 0 means false, okay, F, false, and then low value. Okay, so it's like this. So in a C program, we frequently use the this statement, if statement, like if A equal B. So this is the condition of the if statement. And then we need to check if this condition is true or false. So if this condition is true, okay, then we can represent this true condition as 1 of the digital signal. And then if this is the false, then we can use 0 of the digital signal. Something like that. Also, actually, our digital circuit, CMOS circuit, is working with the voltage level. So it means, so actually, the one of the node of the CMOS circuits are connected to the VDD, is the high voltage. Also, another load of the CMOS circuits are connected to the ground. It's low voltage. So even though real signal of the CMOS circuits is the analog signal, so it means that it swings from VDD to ground. But we can say that if this value is close to the VDD, then we can say, oh, this value is 1. And then if this voltage level is close to ground, 0 volt, then we can say, oh, this is the 0. So usually in the system, we can represent the 0 for low voltage, and then we can use 1 for high voltage. So, and then we call the binary digit. So binary digit means that, so we will learn about the number system in the today's class. So actually we use data systems use binary number system, and then each digit of the binary number system is called a bit. Okay. So, and then one bit can include only 2 values, as I mentioned, 0 and 1. Okay. I think it's some of you already knows. It's very easy. Okay. So now, so we will learn about the number systems of digital systems, and then actually it's not a difficult concept, because so I will explain about the binary numbers. So it's in Korean easy too. I believe most of you already learned about the binary number systems. 중학교 때 배웠나요? 중학교 때 배웠죠? So if we actually, I believe it was already covered in your middle school coursework, right? Okay. This is the logic, or this is the systems handle binary data. I already mentioned. Then how can you represent these binary data? So we can represent, I said that the binary data have only 2 levels, 0 and 1. So which means that we can represent our binary data using binary number systems, obviously, right? Because binary number systems have only 2 values for each digit, right? So obviously we can use the binary number systems for representing binary data. So this is the example. So it's analog sine wave. Then this is the threshold, and then as I mentioned, we can represent if the analog value is over this threshold level, then we can use 1 for representing this value, like this 1, and then we can use 0 for representing this low value. Okay, and then each digit of the binary number system is called a bit. Okay. So actually bit is represent the binary digit. Okay, so that's why a binary digit is called a bit. Okay, and then I think so I already explained about the real world is composed of analog systems, and then we can use analog systems to represent the analog signals. So, but in order to represent the analog signals into the digital signals, then we need to convert the analog signals into the digital signal like this. But we require some criteria for converting analog signals to the digital signals. Okay. Okay. So you can understand like this. So this is the digital system, like DS, but we live in real world, like analog world, right? So actually outside of this digital system is the analog system. But it means actually the digital system receives some data from our outer world and then generate output using the input data, right? But as you know, this is the analog world. So which means the analog signals need to be converted into digital signals. So for example, we can push some buttons on our keyboard where we can push some, so we can touch our touch screen of the smartphone, right? Actually, this action and touching generate some difference of voltage levels, right? So actually, this is kind of it's a simple, but actually the voltage level changes. Voltage level changes if we touch our touch screen or if we push some buttons on our keyboard. So, like the voltage level is changes, then this value is converted into digital signals like 1 or 0. And then this 1 or 0 is given to the digital system. Okay, then the result is generated from the system. Also, if you want to see some output from the digital system, then we can only understand the analog signals because we live in the real world, real analog world. So these digital signals need to be converted into the analog signals. For example, screen is actually you can see the different colors on this screen, but is the analog signal. Okay, so digital data is converted into the analog signals in the output devices. Okay, that's how the system interacts with the real world system, analog systems. So, which means that the analog information needs to be converted into digital data. So, which means these signals need to be converted into the digital format. Okay, like binary number system, and then inside of the digital system, then this system just handles digital signals. So, for example, our file. So actually, file is just kind of digital data, right? And then this file data is put in the SSD or hard disk drive of our computer system. But this data is the format, okay? Because this is the inside of the digital system. But if the digital system interacts with the outside world, real world, then the signals need to be converted into the analog signals. So this conversion is required actually. Okay. So in order to represent the digital data or our normal data, we need number systems. And then in the real world, we use the decimal number system. Right. Then what is the decimal number system? What is the definition of a decimal number system? This is the definition of this decimal number system. The numbers expressed in the base 10. What does that mean? Base 10 means that each digit can have 0 to 9, right? It's a kind of elementary school course. It's just counting. So each digit can have numbers from 0 to 9. Okay, so each digit represents a power of 10. So for example, this is the 5,374, and we can represent this decimal number like this equation: 5 multiplied by 10 to the power of 3, and 10 to 3, 10 to the 3, or 3 multiplied by 10 to the power of 2. So we can represent each digit. So this is the each digit, and then the magnitude of each digit can be represented using a power of 10. That is the decimal number system. Then what is the binary? It's simple. It's the kind of So number each digit, the number if numbers are expressed in the base 2, so which means that each digit can have only 0 or 1, only 2 values. So decimal number system, each digit can have 0 to 9, so 10 different levels or 10 different numbers. But in the binary number system, each digit can have only 2 values, 1 and 0. And then, so which means like the decimal number system, each digit represents a power of 2. Okay, it's the same. So each digit, like each digit is the 2 to the power of 3, right? And then this is this digit represents the magnitude of 2 to the power of 0, which means 1, this is 2 to the 1, 2 to the 2, 2 to the 3. Okay, so this is the binary number system, right? Then what is the power? What are powers of 2? So why do I choose this? So actually, this is very simple. So I believe my daughter can calculate this. So it's 1, it's 2, it's 4, it's 8, 15, blah blah blah. Then why do I show this slide? It's very easy, kind of elementary course. So actually, as a computer engineering or computer science student, if you can memorize the result of the powers of 2, then it can be very convenient. Okay, because we very frequently use the powers of 2 in the data system, also in programming, also in the computer system, because computers can do binary number system. So if you understand, so actually in the real world we use the decimal number system, but computers like the digital world use the the binary number system. So if you are familiar with this powers of 2, then you can easily calculate some numbers from the digital data. So you can understand some structure. Well, you can understand the digital world more easily. So, but it's handy to memorize. So if you memorize the magnitude of powers of 2, then it will be very helpful. But I believe you can memorize easily because we frequently use these numbers 1, 2, 4, 8, and then 10, 24, and 20, 48, like this. Okay. And then number conversion. It's also easy, right? How to convert the binary number to the decimal number. We already know that each digit represents the power of 2. So this digit represents the 2 to the 0, and then this digit represents the 2 to the 1, that's the 2 to the 2. Then this is the 2 to the 4, right? Then we can calculate the magnitude, the decimal number of this binary number, right? It's 1 multiplied by 2 to the 4 plus 1 multiplied by 2 to the 1 plus 1 multiplied by 2 to the 0. Right? You can calculate. And then how to convert the decimal number to the binary. I think you already know because it's actually I believe you already learned about the decimal number or binary number in the maybe middle school or elementary school. Actually, there are 2 methods for the binary conversion. So, which means that we can convert this decimal number to the binary number using these 2 different methods. So the method 1 is to find the largest power of 2 in bits, and then subtract and then repeat. But this method 2 is the more convenient. So repeatedly divide by 2, and then remainder goes the next most significant bit. So you need to understand this terminology, most significant bit. So this is the binary number. 100,011. Then what is the most significant bit? It's called the MSB. It's a most significant bit. So what is the most significant? What is the meaning of significant? The important, right? So because this bit is as the magnitude of this bit is the largest, right? So this bit is the most significant bit. So it's called the MSB. Then what is the least significant bit? LSB. It's this one. Okay. So I frequently use this terminology and MSB or LSB, the most significant bit or least significant bit. The most significant bit is the leftmost digit of the binary number, and then LSB, the least significant bit, represents the rightmost bit of the binary number. Okay. Then how can we apply the method 1 and method 2? Okay, so this is the example. It's a bit victory, and then it's a decimal number. How can you convert this number into the binary number? So easy, right? So if we use the method number 1, then the largest power of 2 is the 32. Then 53 minus 32, then what is it? It's a 21. And then we can repeat then the LSB is the 1, and then this means the 2 to the 5 because it's the 32. So which means that this is the 6th bit of the binary number. And then it's a 21, and then what is the largest power of 2? The 16, and then it's a 1, so it's a 2 to 4. Then we can repeat this calculation, right? But it's not convenient. But then we need to find the largest power of 2 to apply this method 1 for the binary conversion. And then I believe most of you know, so we can repeatedly divide this number using 2. So what's this? 26, right? And then remainder is 1, and then 2, 13, remainder 0. So why am I doing this? 1, 2, 0, 2, 1. So, and then as I mentioned, each digit is the MSB of this calculation. So what is the MSB? This is the MSB. So it becomes the 110101, right? Like this. Okay. We repeatedly divide this decimal number using the number 2, and then these are remainders of the division, and you can just use the last one as the MSB of the binary number, and then the next this becomes the MSB of the next digit. So 110101 is the binary number. So this can be converted to the binary number like this. Okay, it's easy, right? Okay, so let's think about the binary values and then ranges. So what is the ranges? What is the range of binary values? So for example, this is the example of the decimal number. So think like this. Consider the n-digit decimal number. Then how many values can be represented using n-digit of decimal number? So for example, if I need 3, okay, that is n is 3, then what is the smallest value? It's 0, right? In decimal number system. And then what is the largest value? It's 9999. So how many values? We can represent 1,000 different numbers using 3 digits of decimal number, and then it is equivalent to 10 to the power of 3. And then what's the range? Range is the 0 to 999. Okay. Then we can find a rule. It's very simple. So if we use the n digit of decimal number, then we can represent 10 to the power of n different numbers. Okay, and then range is the 0 to 999, like this. So this means the actually 10 to the power of n minus 1. Why? Why do I explain this? So if we use the n bit of a binary number, then how many values? It's the same. If we use the n bit, then we can represent the 2 to the power of n different numbers, right? And then the range is the 0 to 2 to the power of n minus 1. It's the same, right? It's the same to the decimal number. So because the decimal number uses the base of 10, then we can calculate the number of values, and the range of the decimal number is the 10, base 10. And then for the decimal binary number, then we can use the base of 2. So we can also calculate the different numbers, number of different values, and the range of binary numbers is the 2, base of 2. Why do I explain this? So, actually, the computer system is a hardware system. So it means hardware works in the real world, and then in order to represent these numbers, the binary numbers, we need to use hardware resources. Okay, so which means let's think about the memory. So we want to store a binary data in our memory system, like DRAM or SSD. But this memory is a hardware system. So a hardware system has restricted resources, limited resources. Okay, so we cannot use the hardware without limit, because this is the real system. So which means with the 8-bit of the memory, so memory size, if the memory size is 8-bit, then what is the largest value that can be stored in this memory? Because the bit number is 8, the largest number is the 2 to 8 minus 1. So which means that if a memory has 8-bit of storage space, then the largest value that can be stored in this memory is the 255. So the range of the digital data is restricted by hardware resources. Okay, because the hardware is in the real world. But if you So if you use the Python, actually the Python has any data type. So I believe the Python has only number data type. And then I believe you can store a very large number in this variable, Python variable. But if you use a C, actually the C has the more strict data type. For example, integer. Actually, if you use the integer data type, then the maximum number that can be stored in this variable is limited by the size of integer data type. So usually we use the 4 byte. The byte means the 8 bit, which means the 32 bits for the integer data type. So which means and then it's actually unsigned integer. So which means the largest value stored in this variable A, if this A is declared as the unsigned integer, then integer is the 32 bit. And the largest value that can be stored in this variable is the 2 to the 32 minus 1. Okay, this is the largest value that can be used in the C. But in Python, there is no data type. That's why the Python is so easy to learn. But if you use the other programming languages, you need to consider each data type as the available range. It is because actually when the data is stored and handled in the system has limited resources. So actually, if the system can handle a certain range of numbers or certain magnitude of these numbers. Okay, that's why I explained about the range and then how many values of the n-digit binary number system. Okay, we need to consider some restrictions of the digital system or limited resources in digital system. Okay, and then we frequently use hexadecimal number in the digital system. What is a hexadecimal number? It's 16진수, right? The number, if numbers can be expressed in the base of 16. Okay, so then each digit can have 0 to 15, but in a decimal number system, we do not have the one digit number that can represent the 15, so we use alphabet. So A means 10, B means 11, and F means F means the 15. Okay, so each digit can have 0 to 15, but actually we use the 0 to F. Okay, this is 10, this is 11, this is 12. Okay, actually we can apply the same rule for calculating the decimal number system. So each digit represents the power of 16. So this means the 16 to the power of 0, and then this means the 16 to the power of 1, and 16 to the 2, 16 to the 3. You can calculate this number like this equation, the same. Then why do we use hexadecimal number frequently in the digital system or in programming also? So it is because 4 bits of binary number can be compressed. Into 1 digit of hexadecimal number. Right. So if we use the binary number system, like if we represent our number using the 32-bit binary numbers, then we need to use 32 digits to represent this number, like 1, 1, 1, 1, 1, 1, 32 times. or it's very long, then it's not convenient. So we just compress the 4 bits of the binary number into the 1 bit of hexadecimal number. Then this 4 bit can be represented the 1 bit of the hexadecimal number, right? Like this. So, so this is the hexadecimal digit, so 0 to n, and then the decimal number, the equivalent decimal number, and this is the binary equivalent number. So as you can see, 0, 0, 0 of the binary number can be represented into the 0 of the hexadecimal number. So 4 bit is compressed into the 0. And then how about the 1111? So this can be represented using f of the hexadecimal number. So which means if we use the 32-bit binary numbers, then these 32-bit binary numbers can be represented using 8 digits of hexadecimal number. Okay, that's why we frequently use the hexadecimal number. And then if we want to use the hexadecimal number in your programming language, then we frequently add prefix 0x. Okay. And it's easy. Okay. So conversion is also so actually so as I mentioned, if we in a programming language we added the 0x in front of the hexadecimal number. That means the it represents this number is the hexadecimal number. Okay, so you can convert this hexadecimal number into the decimal very easily because each digit represents the power of 16. Okay. Okay. So you can apply. Then let's learn about some unit of the binary data. Okay. So we already learned about the bit. Bit represents the binary digit. So 1 digit of a binary number is called a bit. So for example, this is the binary data 1001, 0110. And then this binary data is the 8-bit data. Okay, I will frequently use this bit or height. So that is the unit of the binary magnitude of a binary number. So each digit represents each digit of a binary number represents bit. Then we can frequently use this is the 8-bit data. Okay, so this 8-bit also means hardware system can have the resources they can handle 8-bit data. Okay, so for example, my memory can have 8-bit. It's very small, right? So my memory can store 8-bit data. So which means that we can store 8 digits of binary number in our memory. Okay, a very small one. So also byte means 8 bits. Okay, and then I believe you frequently use size of a byte. Okay, because this is the basic unit that is used for representing the size of data in a computer system. Okay, so we frequently use bit or byte. So 8 bits means 8 bits are equivalent to 1 byte. Okay, so we frequently use bit and byte. And then nibble means the 4 bits, but it's not frequently used. So we frequently use a bit or byte. And then, as I explained, we frequently use the MSB and LSB. Okay, so in this slide, the LSB is the rightmost digit of the binary data. So this significant bit, and then MSB is the leftmost bit of the binary data. It's the most significant bit. So we will frequently use the LSB and then MSB. And then the 8-bit is the byte, and then 4-bit data is equivalent to the nibble. So then one binary digit is, so we frequently use one binary digit is the 1 bit. Okay, and then one hexadecimal digit is how many bits in binary number? It's 4, right? So we learn it's a 4-bit, and then it's equivalent to 1 nibble. Okay, and then 2 hexadecimal digits makes 1 byte. So for example, what is this one? This is a 1001 and then 0110. So this is the 6 in hexadecimal number, and then 1001 is the B, right, in hexadecimal number, right? So we can represent this binary number in the hexadecimal number like the 0xB6. Okay, so this is the 1 byte of data, and then if we use the 2 digits of hexadecimal number, then this size of this data is equivalent to the 1 byte of data. Okay? So 2 hexadecimal digits make 1 byte. So this most significant byte or least significant byte are not frequently used because we usually MSB for representing most significant bit, and then LSB for least significant bit. Or sometimes we can use the most significant byte and then least significant byte. So which means the leftmost 2 digits of hexadecimal number is the least significant byte, and then the leftmost 2 digits of hexadecimal number is the most significant byte. Okay, but it's not frequently used. So those terminology are not frequently used. We frequently use MSB for the most significant bit, and then LSB for the least significant bit. Okay, and then how can you represent the large powers of 2? Okay, so in the previous slide we also learned the many powers of 2, but actually the modern computer systems handle large amount of data, very large size of data. Okay, then how can we represent those large size of data? So just to memorize it. So 2 to the power of 10 is equivalent to the kilo, like K. Okay. So you may think that in a decimal number system, K means the kilo means actually 10 to the power of 3, the 1,000. That's why we use the in the decimal number system for every 3 digits. But in the digital world, digital systems use binary numbers. Then kilo means actually 2 to the power of It is because 1024 is almost, it's very similar to the 1000, right? That's why we use the 2 to the 10 as kilo. So, which means if we use the 1 kilobyte, then it means the 2 to the power of 10 byte, okay, which is 1024 bytes. Okay, it's not 1000 bytes. 2 kilobytes means the 2 to the power of 10 bytes, so which is 1024 bytes. Then, actually mega means the actually 2 to the power of 6 in the decimal number, but also in the distant number system, the binary number system, 1 mega represents the 2 to the power of 20. So it's mega, giga, tera, then peta, exa. Okay. So then if you see the 1 megabyte, then you can easily know, oh, this is the 2 to the 20 byte. So which is, oh, how can you calculate? It's similar to the 10 to the power of 6, but it's not exactly the same to the 10 to the power of 6. But so you can understand that 1 megabyte is equivalent to the 2 to the power of 20. Okay? And then giga means the 2 to the 30, and then tera means the 2 to the 40. So which means, oh, my SSD, the capacity is the 1 terabyte, which means actually, so sometimes this tera is a different meaning in the storage devices. Okay. My DRAM. So you can say that, oh, my smartphone has 4 gigabytes of RAM. 4 gigabytes. So which means that the DRAM in my smartphone can store 4 gigabytes of digital data, which means giga is the 2 to the power of 30, so which means 4 multiplied by 2 to the power of 30 is the 2 to the 32 byte, equivalent to the 2 to the 32 byte. Okay, so we frequently use the KMGT in the computer system. We can use P, but P is very large. Okay, but we frequently use the K, kilo, mega, giga, and tera for representing by very large data in computer systems. Okay, so this is the this is an example. 2 to the 10 is the 1024, 1 kilobyte, 2 to the 20, 1 megabyte, and 1 gigabyte. So just remember. Okay. Then it's the example also. So what is the value of 2 to the 24? So it's 22. 2 to the 20 multiplied by 2 to the 4, so which is the 2 16 kilo mega giga. Kilo mega giga. Megabyte. Okay, because mega represents the 2 to the 20. Okay. Kilo means the 2 to the 10. The 2 to the 10 is the kilo. K, 20 mega, 30 giga, 40 tera. Okay. So it's a 16 megabyte. Then how large of a value can a 32-bit integer variable represent? The largest value is the 2 to the 32 minus 1. Okay. We already learned the range of binary number. Okay. So it's the same example. So assuming you have 4 GB of main memory in your computer, and how many bits are required to represent the address of the main memory? What does that mean? So address represent the actually in the main memory system, in the main memory of your computer system, the address 1 represent the 1 byte size of data. Okay, so which means if address of 000 all zeros represent the 1 byte of data, and the next address is the 1 that is pointing the next 1 byte of data. So which means the address 1 represents the 1 byte size of data in your computer system. Okay, it is called the byte address, and then most computer systems use byte address for representing their address of main memory. Then what does that mean? Oh, my computer has 4 GB of main memory. Then how many bits are required to represent the address? So I said 1 bit. So one represents the 1 byte of data, no address. Then so 4 GB of data. How many bits are required? How many bits? What is 4 giga? What is giga? It's 2 to the 30. Then 4 is the 2 to the 2. So multiply 2 to the 32. Okay. So that is the size of byte that can be stored in this main memory, right? You can store this amount of data, this amount of bytes in this memory. Okay. Then I said address 1 is mapped to the 1 byte of data. Okay. Then how many bits are required? It's 32 to the 32 byte. So how many bits? 32 bits. Right? No. So with the 32 bits, we can represent the 2 to the 32 different numbers, right? Okay. Using the 32 bit of a binary number. Okay. And then I said that 1 bit, one of the address number 1 is mapped to the 1 byte of data. Okay. And then this memory can store 4 GB of data. So which means each byte need to be identified by different address number. Are you following me? So which means we require 2 to the 32 different numbers to represent the address of 4 GB of memory. That's why we require 42 bits for representing address of this memory. Okay. That's the some example of the binary, so binary representation in computer systems. Okay. Okay, so addition. Why do I this? So because actually you can understand the computer is the enhanced calculator. Actually, the computer also has the very basic arithmetic instructions such as the add, solve, and subtraction, then multiply, and division. Okay, so which means the computer hardware receives the input operands, then computer hardware can generate the result. So let's start from the decimal addition. Then how can we perform the decimal addition for these two different decimal numbers? So you can say that this is an input data, the input value like 37, 34, and then this is another input value like 51, 51, 68. Then how can you perform the decimal addition? So these are two different input, like the input 1 and input 2, and then this is the addition, and this is the result. Okay, so which means this is the input 1, the input 2, and this is the result. Okay, how can you perform the decimal addition? So it's kind of elementary course. So we perform addition for each digit, right? So it performs the 4 plus 8, and then we know the result of 4 plus 8 is 12. So, but we cannot represent the 12 with the one digit of a decimal number, right? So the result of this digit becomes 2, and then how about the 1? This is the another digit. So we need to write 1 on the above of this digit, the 3. So, and then this number 1 is generated from the right digit, right? So this number is called a carry. Okay, because when you perform the addition for this digit 4 plus 8, and of course the magnitude of the result is larger than 9, so we cannot represent this number. So the additional 10 is delivered to the next digit, and then this number is called a carry. So when we perform the addition for this digit, the next digit, then we need to consider this carry, right? So when we perform the addition for this digit, then we need to perform the 1 plus 3 plus 6 is 10. So the 0, and then also carry is generated, and then we also 1 plus 7 plus 1. Why doing this? Why am I doing this? 9. Okay, we can perform the addition for the decimal number system. Then how about the binary? Binary is the same because it's actually we can apply the same rule for the different number system. Okay, so how about this? For binary addition, then we also start from the LSB, the addition in LSB. So the 1 plus 1 is in the binary number. This is 1, 0. Okay, so 1, 0 cannot be represented using one digit of a binary number. So carry is generated. Okay, so this will become 0, and then carry is generated. So we need to perform for this digit. We need to perform 1. One plus 1 plus 1. What is the value? 11. So carry is also generated. So carry is propagated. Carry is delivered to the next digit. Then so we need to perform 1 plus 0 plus 0 for this digit. So by doing this, we can calculate we can perform the addition, the binary number system. So why am I doing this? It's obvious, and then I did it, so everyone knows. So why am I doing this? So actually, so we are learning about the digital system. Then, as I mentioned, a computer is a kind of digital system. So which means the computer receives digital data, which can be represented using binary number system. So which means a digital system receives two binary numbers or three multiple binary numbers, and this the system can generate the output from these multiple binary numbers. So which means if you design a digital system that can perform arithmetic such as the addition, then you need to design your hardware that can perform this addition exactly. Okay, so we already know how to add two binary numbers, but in order to design the system that can perform addition, then you need to also consider these factors. You can say, oh, this is very obvious, but because of this mechanism, the mechanism of the binary number addition, then the hardware may be this hardware may take longer time. So what I want to say is that, we can easily perform one digit of addition, like 1 plus 1. But if we handle very large data, like 32-bit data, right? Because so if we use the integer data type in our C program, then each variable handles 32-bit data. It's a very large data. This data includes very large number of bits. So like A plus B, but this is the 32-bit data, so this is a 32-bit data. Then we need to, and then calculate the result C. Then in order to support this operation, then a computer, a processor needs to have the digital component that can perform 32-bit addition. Okay, then which means this adder, so this the hardware that can perform addition is called an adder. And the adder needs to support the 32-bit addition, which means we start from the LSB and then carry is generated, and then LSB, and next digit. So add operation can be performed like this. Then what is the problem? So you may think that, it's the same to the real calculation. So the machine also the system can perform addition like human. The mechanism is the same. But problem is that we start from this digit, and then until the result of this digit is generated or completed, then we cannot start the computation for the next digit. It is because of carries. Because before this carry is generated from the previous digit, then this digit cannot be performed. Okay. So even though the operation of the operation using the binary numbers are very obvious and it's very easy actually. But if you design digital hardware that can perform the binary arithmetic, then you need to also consider these factors. Okay? That's why I showed the example of binary addition in this slide. So you may think, oh, this is very easy, but it's very obvious. Okay. So I will stop here. Then any questions? Okay, thank you for your attention. Then see you in the next class. Come down.